Today we're going to have a brief overview of acid and base reactions. We will get more in depth with acid and base chemistry when we get to Unit 8. So just a quick review, acid-base reactions are when you have a transfer of a proton. So if we use a really simple one like this, the hydrogen and the sodium ion are going to swap places to form sodium chloride and water. Depending on the acid, you'll form different salts, but it will always form water as a product, which is part of why they're called neutralization reactions. So you could have C2H2O2 reacting with KOH, and you would form potassium acetate and water, like that. Now, be careful with your net ionic equations. When you have a strong acid or a strong base, you want to completely dissociate it in your net ionic equation. But if you have a weak acid or a weak base, you do not dissociate those ions. You would still write aqueous for them, though. So let's review those strong acids and strong bases. For acids, there are 7 strong acids: HCl, HBr, and HI. HClO3, HClO4, HNO3, and H2SO4. Those are your strong acids. That means when you're writing a net ionic equation, you would completely dissociate them. The strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and strontium hydroxide, and then calcium hydroxide. Oh, I already did strontium. Cesium hydroxide, there we go. Strontium hydroxide and barium hydroxide. I knew I got one out of order there. And again, so these are all of the strong ones. So if you were writing a net ionic equation, you would split them up into their ions. So on the previous slide, when you had the HCl plus NaOH yielding sodium chloride and water, all this HCl would dissociate because it's strong. The sodium hydroxide would dissociate because it's strong. Sodium chloride is a soluble salt. It's a group 1 metal, so that dissociates. So you'd wind up with hydrogen ions and hydroxide ions form water. That's your net ionic equation. And that's true for your net ionic equation anytime you're reacting a strong acid with a strong base. However, if you look at that other example I gave, which was the acetic acid, which is vinegar, with potassium hydroxide, and that will form the potassium acetate and water. The acetic acid is not one of those 7 strong acids. So you would leave it together in your net ionic equation. We would still label it aqueous, but you would not split it up into the ions. Potassium hydroxide completely dissociates, and potassium acetate completely dissociates. So potassium is a spectator ion, and you're left with just the acetate ion and water as your 2 products. And so this is your net ionic equation, and I'll write it in the states when you have this. So be very careful when you have strong acids, completely dissociate. If it's not on the list of strong acids or strong bases, then you do not completely dissociate them. Okay, we're going to talk now about conjugate pairs. So if I start out with an acid like HCl, we can form what's called a conjugate base. And a conjugate base is formed when an acid loses its hydrogen. What's left over is called the conjugate base. And the stronger the acid, the weaker the conjugate base. All right, let's do a couple more examples. If I have that acetic acid, its conjugate base is C2H3O2. Water can actually act as an acid. When water loses a hydrogen, you're left with just OH, and that's its conjugate base. So these together would be called a conjugate acid-base pair. Now let's look at some bases. If I have something like ammonia, the conjugate acid is what happens when the base gains a hydrogen. So it would be NH4+ would be the conjugate acid for ammonia. Or if we have if we have water, water can also act as a base. When water gains a hydrogen, it forms H3O+, which is called hydronium. Or you could use that hydroxide ion or any of these ions from the previous example and add a hydrogen, and you'll get water there. So any of these things are considered conjugate pairs. Conjugate pairs have just one hydrogen difference. And the substance that has the additional hydrogen will have a one larger charge than the substance that has the fewer number of hydrogens. So here's an example of ammonia and water. Ammonia is a base. Now, it doesn't look like your typical base because it doesn't have the hydroxide ion in it. But we know that this is a basic thing because when it reacts with water, it forms those hydroxide ions. And whenever you see the OH being formed or released, you know it's a basic solution. So the ammonia is a base. We can also tell that it's a base because over the course of the reaction, the NH3 will gain a hydrogen. And when it gains a hydrogen, it becomes ammonium, and that becomes the conjugate acid. So the base gains an acid and becomes the conjugate acid. The base gains a hydrogen and becomes the conjugate acid. Now, water, on the other hand, must be acting as an acid. Water is what we call amphoteric or amphiprotic, depending on your textbook. But either way, it means it can act as either an acid or a base, depending on the scenario. In this scenario, ammonia is acting as a base, so therefore the water must be acting as an acid. And acids will lose their hydrogens to become the conjugate base. So the hydroxide here is the conjugate base because it has one fewer hydrogen and one lower charge than the hydroxide. And so that's how you answer those types of questions where you have to identify acids, bases, conjugate bases.